Good morning, everybody. So as we get started today, I want to talk a moment about what our grades are looking like in the class and kind of what grades we tend to see once we get to the end of the semester. Like for lab, homework, recitation, we kind of project scores, right? Because we don't know what these scores are necessarily going to look like because there's lots of labs and homeworks and stuff that are ungraded. But typically by the end of the semester, labs are in that probably about 85% range. Homeworks and recitation are always very high. I mean, recitation, you go, you get the points. Most people go. We have a few students who might miss from time to time, but the averages there are typically in the high 90s. And then the midterms, of course, are in some ways, unfortunately, lower averaging. Midterm 2 came in at about 67% was the midterm 2 average. I talked a bit about how chapters 4, 5, and 6 were a little bit trickier than chapters 1 through 3. That doesn't always mean scores have to coincide. This semester, the scores coincided with the material being a little harder. I think the test was slightly on the longer side too. But midterm 3, I think we definitely have a chance to rebound midterm 3. 7, 8, and 9 are a little bit more in a cohesive fashion. The chapters build on each other a little bit better than the midterm 2 chapters did. So I hope we can rebound as a group and do better on midterm 2, on midterm 3. And what we should always think about in any class, anytime you get a score back, is just, even if you got a 92%, you might think, how could I have gotten a 96%? If you got a 78, you might want to get your score in the 80s or 90s. And I think it comes down to, how do you use the book? How do you incorporate problem solving into your studying? How often are you doing these things? And I think the more often you guys come to class, this is preaching to the choir for those that are in person here today. But coming to class, or at least watching the lecture video before the next lecture takes place, is great. I think sometimes it's easy to fall in the habit of, not for you guys maybe, but for those that are at home, of waiting until a week before the test to start watching the lecture videos. It just becomes a volume problem. There being too much content to learn in a relatively short period of time. And then the other problem I think that students encounter is you see a practice test, you think, okay, this is a set of problems I need to figure out how to do, and then you go figure out how to do them, and then you move on maybe and do that for another practice test, and you have a set of problems like, okay, I don't know how to do half of these, but I'll figure out how to do them and make progress. But that's actually not a great way to think about learning. The practice exam is meant to be a chance for you to solve the problems authentically, like a test-taking scenario, and to see how you would really do. It's not to see a set of problems that you need to go figure out how to do. There are a set of problems you should already know how to solve by the time you're looking at a practice exam. Now, to get an A, I think, is a 92 and up, and an A minus is an 88 and up. So it's not like you have to get 100%. And especially with the lab and homework items being relatively high averaging, if you're pulling a high 80s exam average, I think you're going to see that your final grade should be in the A range, A solid range. So it's not like you have to be perfect every time on your studying or on the real exam. But I think the more you push yourself to look at the practice test as an assessment, and then like daily quizzes as a mini assessment that you can take before you get to those practice exams and real exams, that those are problems meant to take you away from the textbook and to use your own problem-solving abilities and knowledge to solve those problems. And like I've mentioned this a few times before, I think becoming really reliant on a textbook, Google, classmates, tutors, whatever your resources are for figuring out problems on homework or a practice exam, if we're using a lot of resources for those things, we're going to run into a problem on the real test when we don't have those resources available. So that's why we just got to get a lot of space practice of doing problems where maybe we don't know what section we're in. Sometimes a test question comes up, we don't know if it's chapter 5 or if it's section 4 or 5 out of chapter 5. When you do a homework problem out of the book, you know what section it comes from. So like a test problem is always a little bit harder because you have to think, what section is this from? What equations matter? What's the context of the problem? And all those things, the more you practice, the better you're going to get at those things. So midterm 3 in the final, I fully anticipate will rebound, and our scores will go up, not down for those. So if you're a little jaded by your exam score, I would say make sure to think about where your actual grade is and not to overly sort of get anxiety over one exam score. Midterm 2 is 14% of the class. That's really not that much in the scheme of things. 14% for midterm 3, 20% for the final. So a lot of ability to make ground up. And then also there's 38% of the classes up here, which is already averaging in like the 90% range. So keep working, keep going to recitation, keep getting your homework points, try to learn as much as you can through the homework assignments, and then obviously keep going to lab. So like don't get frustrated because you got a low exam score and skip lab for the week. Sometimes that happens because we get frustrated. But so just take frustrations out in the textbook and read it more. I don't know. Like, I don't know what else to do other than that. And sometimes really reading the book is annoying and tedious, but it is maybe the one thing that helps us put all the ideas into context and helps us try to internalize those ideas. Okay, so I don't want to take up too much more class time with exam and point discussion, but as we head into midterm topics, we'll just try to move forward and do our best to get the best possible score on midterm 3. Okay, so we were talking about ionization energy last time in chapter 7. And ionization energy, one of the things we're talking about was the first versus second versus subsequent ionization steps are the idea of something like sodium losing 1 electron to go to sodium plus versus losing a second electron to go to sodium 2 plus. Now, you don't see sodium 2 plus in nature. You can kind of see why, is because it takes way too much energy to lose that second electron. The second electron lost from sodium would represent a core electron. So we're going from sodium to sodium plus an electron. So we're losing that 1 extra valence electron that sodium had. That seems, you may have thought that would be negative. You may have thought that this should have proceeded exothermically, and it still requires energy. It still takes energy to remove a negative particle attracted to a positive nucleus. You have to break that plus-minus attraction, and so energy has to be applied. But for the alkalis, we're going to see the alkali group is the lowest ionization energy from left to right. As we go from left to right, we're going to see that ionization energy generally increasing as we proceed to the next element. Like, notice the first ionization of magnesium is higher than sodium. We mentioned that there's a bit of a zigzag with the trend. We'll talk about that in a minute on why aluminum isn't higher than magnesium, but we'll come to that in just a moment. But we get this general increase in the ionization energy from left to right. But let's talk about the second ionization energy. So that's losing a second electron to go to sodium plus. If we're talking about magnesium, magnesium can go to magnesium plus, and then it can lose a second electron to go to magnesium 2 plus. And you can go to magnesium 3 plus and calculate the energy associated with losing that third electron. Well, the third electron loss for magnesium is the one that's really high, because that's the one that starts to remove a core electron. So you're removing the outermost electrons first. You pluck off an s electron, the other s electron, and then the third electron from magnesium are one of those 2p electrons closer to the nucleus, experiencing a higher charge, requires much greater energy to remove. And so each successive electron requires more energy than the previous. So the second ionization energy of sodium is particularly high because it's removing a core electron. But notice that the second ionization is always higher than the first. Like, if you inspect the second, it's always higher than the first ionization energy for every element, because once you remove 1 electron, the other electrons are less repelled by the other electrons, so they get a little bit closer to the nucleus, and then takes more energy. They're closer to the nucleus, takes more energy to remove them. So the ionization energy is breaking the negative-positive electrostatic force of attraction. And so if we come back to Coulomb's law, so our energy of electrostatic attraction is equal to kappa Q1 Q2 divided by D. If removing an electron makes the other electrons closer to the nucleus, we shorten their distance of separation, and that shortening the distance of separation is increasing the energy of attraction. It's increasing the magnitude of the energy of attraction. The reason why I put the bars here for magnitude is if I'm thinking plus minus here, technically it makes the energy more negative, and we have to apply more energy to break that attraction. So if we think of our energy, it's like negative in terms of where the energy is. So if I think of the magnitude of that energy difference, it's a greater magnitude the closer I make the charges. So if you have a positive charge and a negative charge that are really far away, not as good as if you make them closer together. So the closer you can make charges, more attracted, more energy required to separate them. And then likewise, if you can increase the magnitudes of charge, so if you increase the magnitude of charge, again, I like to think of the absolute value, because a -2 charge is greater than a -1 charge as long as you're talking magnitudes, because -2 is more negative than -1, right? So we can probably agree that -2 is actually smaller than -1, but the magnitude of -2 is greater. So the magnitude of charge is what matters. Increase the magnitudes of charge, you also increase the energy of attraction. And so the increasing the magnitudes of charge is why, going left to right, magnesium is smaller, so that's good here. And then magnesium experiences a greater effective nuclear charge. So it gives it a greater magnitude of charge. Both of those means it should have a greater ionization energy. Okay, so once we remove all the valence electrons, it takes a great deal more energy to remove the next core electron. So as soon as we start removing core electrons, you go from valence shell to core electrons, closer to the nucleus, much closer, and experiencing a much greater charge. Okay, now let's try to get to this like zigzagging effect, and so let's talk a little bit in general too of how our left to right trend generally increasing. We get a periodic inconsistency though. So we go from lithium to beryllium increases. We actually drop a little bit to boron, then we go back to increasing, drop a little bit to O, then go back to increasing. And this becomes what we call periodic. So we get this periodic inconsistency where it's the same trend of two go up, then one goes down, and then the next two go up, and then down, then up. And now you may wonder why this trend exists, and the trend exists really because of just what I would call an anomaly with the configuration that these elements have. If we start thinking about our configurations, these are ns2s. So we have electrons in an s orbital, and then the outermost electrons here are in a p orbital. So we have the np1, the np2, the np3 group for boron, carbon, nitrogen. So the boron group is an np1, meaning they all have the outer configuration of a p orbital. Now, the difference between a p orbital and an s orbital is a p orbital is a little bit bigger. So a p orbital just happens to be bigger than an s. As you go from left to right, you would imagine the s orbital is going to be shrinking every step of the way. But then when we go from lithium to beryllium, then we go to boron, all of a sudden we have that bigger p orbital. So the issue with boron is it's just removing an electron from a bigger orbital that has a smaller attraction due to just the electron on average being a little further away from the nucleus. And so it's kind of like not doing an apple-to-apple comparison. If you wanted to compare, you can do experiments that can show you what the ionization energy would be from the s orbital. From left to right, you get a periodic, or you get the increase in ionization energy without this inconsistency. So if you said, well, how much energy does it take to remove the ns2, how much energy does it take to remove the s electron from boron? It's greater than magnesium, as you would expect. If you want to remove the s electron from oxygen, it's greater than nitrogen, as you would expect. So if you remove the same electron from the same orbital from all of these elements from left to right, you get the increase from left to right without any break in trend. So the break in trend for boron is just because we're removing from an np1 instead of an ns orbital. So we're moving an electron from a p orbital instead of an s orbital, and the p orbital just is bigger and has a different sort of trend and property than the s orbital. And then when we get to oxygen, it's a little bit lower in ionization energy because we've actually spin paired the electron in the orbital that's being removed, and that causes a little instability. So we destabilize an orbital by spin pairing the electron, makes it easier to remove that electron. And so for oxygen here, the issue is it's this configuration, and this destabilizes the orbital, makes it higher in energy than the other two orbitals, makes it easier to remove one of those electrons. And so due to electron pairing and the instability of the electrons that are then paired together, you relieve that pairing energy when you remove the electron. And so then when you go to fluorine and neon, they have spin paired electrons, but they're closer to the nucleus, more positive nucleus, so we continue the trend of increasing. And so the issue with our inconsistency is that we just have what I would say is a configuration anomaly. As you go from left to right, you're just from the beryllium group to the boron group, you're going from an s to a p orbital. So you're removing a p orbital, which has a different energy associated with its removal than an s orbital. And then when you go to the oxygen group, you're removing a spin-paired electron, which has a different energy associated with it. And none of the other electrons, technically the s electrons were spin-paired here, but that's maybe not worth dwelling on too much. But the p orbital being spin-paired was bad for oxygen, lowered its ionization energy from where we might have expected it to be. And so we get this periodic trend of increasing, but the np1 group being lower than we expect, and the np4 group being lower than we expect. Now notice the top to bottom trend is generally decreasing. So if you look from top to bottom for like the alkalis, the noble gases, you see that the ionization energies are dropping. Now this is actually a somewhat complicated trend to compare because we have two counter-opposing trends. If you think from top to bottom, if you're thinking of your energy of electrostatic attraction, kappa Q1, Q2, divide by D. If you think about the D term, that's probably the most obvious one. As you go from hydrogen to lithium to sodium, you're increasing the size. So the outer valence electron is moving further away from the nucleus as you go from top to bottom. So from top to bottom, we get an increase in the size of the atom, which is putting the valence electron further away. That trend would predict that our electrostatic attraction should drop from top to bottom. And so just looking at the size trend of atoms from top to bottom would lead us to predict that the ionization energy should decrease, and that seems to be the trend that we most observe. I'll point a few elements out in a minute that don't decrease as we expect, but the other counteropposing trend is the effective nuclear charge trend. As you go from top to bottom, if you recall, the effective nuclear charge does actually increase. And so the charge of one of these being the electron, the other one being the effective nuclear charge, if the effective nuclear charge is increasing from top to bottom as you go down a group, then that would make you predict that the electron attraction to the nucleus, the energy to remove it, should actually increase. And so this trend here would actually predict that we would be increasing in our attractive force, our magnitudes of attraction, and should therefore take more energy to remove the electrons from top to bottom. Now, you can actually see which one wins out when you look at their ionization energies. You can see that it's the distance term that wins out. So most often, it's the size of atoms increasing that controls the trend, and it wins out, and you get a greater change in size than you do increase in charge. So if you recall, the effective charge trend, we said that the Z effective slightly increases from top to bottom. So we get a small increase in the effective charge from top to bottom. We get a pretty big, though, change in size as you go from top to bottom. So it's this size trend that wins out. And so from top to bottom, I know I've written a bunch here. Let me erase some of these lines that went through the writing. But the top to bottom trend generally decreasing due to the increase in size, despite that slight increase in effective nuclear charge. Now, you can look at the effective charge increase and reason out that for like tin to lead, you get an increase. So how could you ever get an increase from top to bottom for like lead being higher than the element above it on the periodic table? And the answer is that for some elements, the increase in effective charge is going to be a bigger magnitude than the increase in size. And you see this with like the sort of third transition metal series being higher than the elements that came before it. So there are some elements that don't follow the general trend of decreasing ionization energy, but for the most part, our main group elements being the S block and the P block, for the most part, with relatively few exceptions, are following this general rule of decreasing ionization energy. But it's nice, I think, that we can see some elements do actually increase from top to bottom, and we can reason out for them it must be, well, for those elements, it must be a smaller increase in size, but a greater increase in the effective charge trend.
Going to NP3 to NP4, there's a decrease. Would you expect the similar decrease when go from NPF?
No, like why doesn't it continue to F and neon? Is that your question?
The question is iron, rubium, and argium. Should they be decreasing compared to manganese?
Oh, like here. Well, that's a good question. I think we don't talk too much about the trend. In fact, I've never really thought too much about why there's a peculiar trend for the transition metals. I don't know if I have a good answer on why iron would be higher. That's a good observation, is why is iron that has the D6, where molybdenum's a D5, why would iron be higher? The issue here is probably, and this actually gets at a topic we're going to talk about in a couple slides, is how do you come up with the electron configuration of cations? And it turns out that we're actually going to remove the S electron first from iron. So the easiest removed electron from iron and transition metals are actually the 4s2, the 2 electrons in the 4s orbital. And so for transition metals, it's if that's the orbital that's biggest, they're going to be the easiest to remove electrons. And so I think the reason why iron is going to be higher is probably just because it's smaller than molybdenum. And so it becomes more of a size trend. So let's kind of come back to that thought a little bit later. And I think 3 or 4 slides we talk about configurations of cations, and we'll go through some of their rules. But I think it's just that we're not removing the d electron is why the transition metals. But I wouldn't worry too much about the trend for the metals. We're mainly focused on the S and P block group elements. But good observation, good question. Okay, and so let's review a couple things or come back to some ideas. One is the idea of isoelectronic series. So if you're comparing ions that have an equal number of electrons, yep. And so here, this is just kind of going back to having 10 electrons for all these ions here. Allows us to compare their sizes based on the number of protons. So oxygen's element number 8, so only has 8 protons. Fluorine has 9. sodium 11, et cetera. And you can see that the more protons you have with the same count of electrons, so each of these ions has their effective, well, their nuclear charge, 1s orbital, 2s orbital, and 2p set of orbitals. You can imagine that if the atoms have the exact same set of orbitals, the one with more charge is going to pull those electrons in more closely. So the smallest of these ions is aluminum, and then the biggest of these ions is O2 minus, and they just follow suit by the proton count. So just a summary on the isoelectronic series and seeing a comparison across 5 ions that share 10 electrons. Let's kind of use the idea of size. So like a question like this one here, we could go back to our bond chart that has the size of atoms and actually predict bond lengths. But what I like to think about with this question here is, can we approximate or rank order the bonds in something like ethanol from shortest to longest without using a specific chart and looking up their bond lengths? So a question like this is kind of getting at, how can we think of the position of the elements in the periodic table? Hydrogen's in the first row, and our second row is carbon and oxygen. That hydrogen definitely is going to be the smallest of these 3 atoms, but is carbon the next smallest, or is oxygen the next smallest? And our size decreases from left to right, so oxygen is smaller than carbon. So when we're putting our bonds together for ethanol, we probably remember the basic Lewis structure. And the actual task of sketching Lewis structure for molecules comes up in the next chapter, in chapter 8. So in chapter 8, we'll talk about how we can sketch these Lewis structures. Let me write this a little more clearly. So if you're thinking of this molecule here, which bond do you think is going to be shorter? The CC, CO, OH, or CH bond? You start to think, well, having the smallest atom is going to make the bond probably the shortest, right? So it's either going to be the OH bond or the CH bond that's the shortest. So oxygen just being smaller than carbon will make the OH bond shorter. So we can predict that the OH bond should be shorter because it has the 2 smallest atoms bonded together. And then the longest bond should be the 2 biggest atoms bonded together. So the 2 carbon atoms should make for the longest bond. And so then you could use a chart like the bond length chart and approximate what these bond lengths should be equal to, or you can just rank order them in a question like this. Yeah.
I'm lost, Doctor. Why O and C are reversed? They in there is reverse.
What's that?
The oxygen is after the periodic table than carbon, but you wrote H less than O less than C. Should be other way around.
No. So hydrogen is definitely the smallest. Do we agree on that?
Yes.
Okay. And so then oxygen versus carbon, left to right trend, we get smaller as you go towards fluorine. So as we go from left to right, we decrease in size. So oxygen is smaller than carbon. Yeah. So it's if you go back to like lithium or something, if you go to hydrogen directly above lithium, hydrogen is smaller than lithium, but lithium bigger than carbon, bigger than oxygen. So like if we're writing like lithium, lithium's over here, which kind of connects in direct line with H to lithium and across the other elements. Okay, so having the 2 carbons bonded together makes for the longest bond. The CO would kind of be the next longest, and then the CH the next shortest. Okay, so we're looking at the OH being the shortest and then the CC being the longest. And the key here is a question like this is getting this right without having to go back to the bond like length chart. Like the question like this isn't meant to look up the precise bonding atomic radii for these elements and add them up. We could do that. We could go to that chart and come up with an approximation for what these bonds should be equal to in their length, but we can also just predict them in a question like this one. All right, let me send this question to you guys for a minute or two to think about this one. So just in terms of effective nuclear charge, so think about your general trends from left to right, top to bottom for these elements here. I'll give you guys a minute or two. This one's probably, hopefully pretty easy. It's just more or less maybe remembering the trend from last time. But the idea from left to right is that our core is constant. They're the only electrons that do most of the screening. So you look at sodium, you have 10 core electrons, 1 valence electron. And for chlorine, you have 10 core electrons as well, and you have 7 valence electrons. And so having that same core, but then with the higher Z, so you have 17 protons versus 11 protons for sodium, more of that charge of chlorine makes it out to the outer valence electrons, and so that's going to increase the effective nuclear charge for chlorine, so it experiences a greater charge and is hence smaller. And so the Z effective from left to right then leads to that prediction that our bond length should decrease and the prediction that the ionization energy should increase. Again, we get that goofy periodic trend due to some issues with configurations, but generally we can think about how charge and size impact the attractive force of the electron to the nucleus. And then for iodine versus chlorine, it's again just kind of like maybe remembering, but it's the fact that the core electrons, as they're bigger, don't screen as effectively, so more of the charge leaks out for larger atoms. So we get a higher effective charge for iodine compared to chlorine, because we get an increase from top to bottom. I guess we're comparing fluorine versus iodine. So it's iodine that has the greater effective charge, not fluorine. And it's just due to the bigger core electrons in iodine not screening as effectively, letting more charge through. But then seeing that an increase in effective charge didn't really help us with predicting the ionization energy trend. The ionization energy trend follows the size trend from top to bottom. So here we'd have chlorine and iodine. So I for the first one, chlorine for the second pair.
Is Z effective 3 minus 36?
Well, the approximation, like so if you approximate effective charge as being the Z minus the number of core electrons, you have to remember this is an approximation, and the approximation breaks down more the larger those core electrons are. So the larger n orbital that those core electrons are using, the greater the error is in this approximation. And so this approximation is just breaking down as more as the elements grow bigger. As you go from top to bottom, that approximation is breaking down. So the other thing I like to come back to, if you go to Z minus S, where the most S can ever be is the number of core electrons, you're just not getting as high as S can be. So S is not as great as it can be when the core is bigger, if that makes sense. So predicting size trends, like this one might be overkill, but maybe not, I don't know. This is like interesting, like right now in class this might be easy, then in like 3 weeks on a test this might be hard, I don't know. So why don't I give you guys a minute to work on this one. So who thinks the answer is C? Who thinks the answer is D? I think the answer is D. Anybody does not know? Who's like totally clueless? Who thinks it's A? I didn't see a lot of hands for C. Who thinks it's B? A couple hands for B. Okay, I think a lot of people are just like, oh, I'm not putting my hand up for any of those questions. That's fine. So the answer here is going to be that chlorine's smaller when we're comparing just with their full number of electrons from their neutral charges. And that's just coming from sodium is smaller than potassium, but then sodium is bigger than chlorine. And so for comparing, potassium has to be bigger than sodium, but then sodium is bigger than chlorine. So chlorine has to be the smallest when we're comparing these uncharged atoms. So following our size trends from top to bottom is where we get this trend. So potassium being bigger down the group makes it bigger, and then left to right trend, chlorine being more to the right of sodium makes it smaller. So chlorine is the smaller of the two, and then K plus versus Cl minus is 19 plus versus 17 plus, where these both have 18 electrons. So isoelectronic series, we're comparing the number of protons, so they have identical configuration, so having more protons makes K plus be the smaller of the two, so K plus is smaller. Okay, so like I said, this question might be easy now. Hopefully it's easy now. But hopefully it's easy in 3 weeks still. It's just, practice it a couple times, I think. This easy question. That size trend of the K plus or Cl minus, I don't know why that trips so many people up on a test. But it's, like you can see here, it's pretty easy to solve. Okay, so the ionization energy trend here, the NP1, NP4 generally break the left to right trend, but for the expected reason, this is again for the NP1, the NP orbital being easier to lose an electron from than the S orbital, and then the spin pairing. So it's, if you go from magnesium, loses from the 3s2, and then if you look, the next element, aluminum, goes from a 3s2, 3p1, so it's easier to lose the electron out of that 3p1 orbital than magnesium's 3s. And then when you get across to sulfur, being a 3s2, 3p4, it's about the spin pairing problem. So the relieving of that pairing energy that was paid to pair the electrons together makes it easier to remove that electron. And then the if you go to the next element, if you go to chlorine, and say, well, why wouldn't chlorine be equally as, like, why doesn't it follow the trend of decreasing in ionization energy like sulfur did? Well, because if you compare sulfur to chlorine, you go from a 3s2 to a 3p5, you then spin pair a second electron. Whoops, I did a third electron. So you spin pair 2 electrons, but now chlorine's smaller, experiences a higher charge. So you spin pair an electron, but you made it closer to the nucleus and more positive, so it's harder to remove that electron, takes more energy. So if we go back, let me see. I hate going back because the way the lecture is recorded, it's hard to go back. But if you go back to the chart that had the I1s, the I2s, the I3s, the I4s, if you look at that chart, you can see that one, we said before, you get the successive increase for each electron that's removed. But if you look for sulfur to chlorine, you can see that chlorine requires a little bit more energy than sulfur did. And then argon continues the trend and requires even more energy than chlorine because it's smaller and experiences then a greater effective charge. Okay, so let's get into the configuration of ions. We're alluding to this earlier. For cations, the electrons are first lost from actually the largest orbitals. And the only thing that's confusing is sometimes this isn't the order that the electrons were put in the first place. So when we look at calcium, this is actually very ordinary to come up with this configuration. It's not hard to come up with calcium's configuration, I don't think. Because if you think of calcium neutral without the 2+, you'd have the argon configuration followed by a 4s2. So you have, like, what other electrons would you remove but the 2 valence electrons? So for calcium, it's really easy to kick those 2 electrons out for the 2 electrons removed to go to calcium 2+. So you go to calcium 2+, you just go to that argon configuration. In fact, that's why we were saying K plus and calcium 2+ and things in the alkali and alkaline group form +1 and +2 cations, is because they're just going to that noble gas configuration. So pretty straightforward for something like calcium. When we get to iron and we get the things in the transition metal block, it's actually maybe not what you expect. But if you follow this rule, it is exactly what you expect from the largest orbitals being lost first. So think about the neutral atom configuration first when you think of a cation configuration. So think iron 0. So iron with the neutral charge would be argon, 4s2, 3d6. Okay, and so if you remove the largest electrons have the largest n value, so n is proportional to size, so the outermost electrons are going to be the 4s. When we were thinking of the configuration, if we go all the way back to like the 1s and do the full configuration of iron and think about where these electrons are for an iron atom, for iron you might be thinking, okay, you have the 26 plus nuclear charge is the Z of iron, then you would have the 1s orbital, the 2s orbital, the 2p orbital, And I'm not going to try to draw the p orbital sticking straight out of the page. Then we'd have the 3s orbital. Let me write in these s's. That's the 3s, the 2s, and the 1s. And then we'd have the 3p. So that gets us to the argon configuration. Then we'd have the 4s. And then that d, I'll use a different color, the d orbital starts to fill in the space here. So the d orbital is definitely smaller in space, closer to the nucleus. Closer to the nucleus is harder to remove. Now, it wasn't filled in first because there's actually more so it becomes an electron repulsion problem versus space problem. Like for calcium, when it was going to calcium 0, it's like calcium was deciding, do I want to put the electrons here, or do I want to pack 2 electrons closer to the p orbitals? And for calcium, it was like, well, there's not enough nuclear charge to put 2 electrons closer to the nucleus in d orbitals. But for something like iron, it's like, actually, it says, well, why don't I lose those bigger electrons first? Like I've already packed the electrons into the d orbitals. Why don't we just leave the d orbitals there and lose the s electron, the larger electrons first? And so if you're thinking of the energy of electrostatic attraction, it seems to fit the idea that the electrons further away are going to be in larger orbitals that have a lower energy of attraction, hence be easier to remove with less energy. So it's going to take more energy to remove the d electron than the s electron, that 4s electron. So the rule for cations is we're going to remove the electrons from the largest orbitals first. Those are the ones with the greatest n value. If you have multiple orbitals that share the same n value, it's the one with the greater L value. We'll give an example of one of those in a minute. But for iron 2+, we're going to lose the 4s electrons first. Those are the largest orbitals. So we lose the electrons in the order of n value with the largest L value. So that would be the n equals 4 being lost before the n equals 3 orbitals, or the n equals 3 electrons in the 3D. And so we lose the 4s2, so the configuration of iron 2+ would be an argon 3d6. Now if you think of molybdenum being a 4s2 3d5, going back to Edwin's question earlier, which was why was iron higher in ionization energy, I think you can probably see it's because iron's probably a little smaller than molybdenum and experiences probably a little bit of a higher effective charge. Now, there's some other nuances from left to right in that ionization energy trend that I'm sure we could explain, but I'm not going to worry about trying to go back to that chart. There's a few cases, like I think nickel is weird in terms of its ionization energy. But it kind of comes back to thinking of, well, what's the configuration of the ion versus what's the size of the elements surrounding it? I think that would help us figure out those. Now, for iron 3+, where's the next electron going to come from? Well, probably the next valence shell orbital, right? So the iron 0, we would have said, had 2 + 6 valence electrons. So you can imagine that you should be removing valence electrons before core electrons. And we're going to remove the next valence shell electron from the d shell. So we're going to remove one of these d orbitals. So iron 3+ removes one more electron. It would be an argon 3d5. Now, we'll do some more examples, things like, lead are interesting that are in the main group. So let's look at some examples of that in a minute. But let's talk about anions first. Anions are actually very easy because we just keep filling electrons in the order you would think. So cations just don't remove the electrons in the order you put them in. So notice when we were doing iron's configuration, we went 4s2, then we counted 6 off into the d. We just don't remove 2 or 3 from the d first. So just notice for cations, we're removing in a different order than we filled them in. In some cases, like calcium was the order we filled it in, but iron wasn't. And then O2-, N3-, argon-, these just continue along like oxygen 0 being a 1s2, 2s2, 2p4. So adding 2 more electrons just goes to a 1s2, 2s2, 2p6. So we just add 2 more electrons. Not so surprising. 3 electrons into nitrogen give it that same neon configuration as well. And then argon minus would just continue putting electron into the next orbital. So this will have the same configuration as potassium, the next element on the periodic table. So this will be, you could say it's an argon followed by a 4s1. So it's just argon's configuration, and then the next subshell being the s. Let's talk about electron affinity, and let's go back to a couple cation configurations afterwards. So electron affinity is the energy associated with an atom absorbing an electron. And so the reaction for electron affinity is an atom absorbing an electron to go to A minus. So we're absorbing the electron in. And so the most favorable of these you would probably imagine would be the halogens, because they're the smallest from left to right, and they're the smallest that have room for one more electron. The noble gases are probably the worst, right? Because while being the smallest and having a relatively high effective charge, they got to throw their electron into a higher energy subshell. And so they really don't have an open subshell that's relatively low in energy to put an electron into. So these are particularly bad at adding an electron, not surprisingly. And then the halogens are the best. So halogens are the most favorable. They have the most negative of the elements from left to right. And so then they're most favorable because they're the smallest, have the highest effective charge, and they have room for an electron. And so fluorine, 1s2, 2s2, 2p5, has that open valence shell for one more electron. It's the smallest from left to right in its group. And then it has the highest effective charge of the elements that have room for an electron. You could argue the noble gases have a higher effective charge, but they just don't have room in a subshell for that extra electron. So from left to right, the halogens are the highest effective charge trend with room for that electron. So the next most favorable group you can imagine, probably the neighboring group, oxygen's group, is also relatively favorable. Nitrogen as well, though nitrogen itself not particularly favorable. Not entirely sure why, but generally speaking, you get relatively favorable in terms of nitrogen here. I guess the nitrogen group, what we're doing here is we're spin pairing the electrons. So the problem with nitrogen is that we're taking what was 3 relatively happy electrons that are spin paired, and we have to pair that electron up. And so the pairing energy is going to make the nitrogen group not as favorable as the preceding group, the carbon group. So carbon group, if you notice, is a little bit more favorable than nitrogen because it doesn't have to spin pair the electron. So nitrogen group here is spin pairing. So we get a little bit of an anomaly here with our NP3s being a little bit not as negative as you might have expected, kind of following in suit with the NP4s not being as high in ionization energy. So NP3 is not as favorable in electron affinities as we would have expected. And then carbon boron, relatively favorable, still negative generally. And then the beryllium group is particularly bad because now we're filling electrons in from what was an s orbital into a p orbital. So the ns2s have to put their next electron into the np group. And so the np subshell higher in energy, so it takes a little bit more energy for the beryllium group. So relatively favorable from left to right, but not very favorable though for the ns2 group and the np3 group. Kind of the opposite of the ionization energy where it was the np1 and 4. So lose an electron from those, ns2, np3, not as negative as we would expect. So we're becoming more negative towards the halogens, and then we're not as negative as you would expect, and sometimes positive for the beryllium group and the nitrogen group. And so then the top to bottom trend is a little bit nuanced, maybe not worth talking about. Because it's kind of interesting that fluorine is not as negative as the second group, the second row, or actually it's the third row. The chlorine group is more negative. Chlorine has a more negative electron affinity than fluorine, but then bromine is not as favorable. If you think about this, this is kind of peculiar because we have the counteropposing trend of fluorine being smaller, but not necessarily with the highest effective charge. And then you have iodine being a lot bigger, but higher in effective charge. And so you may have said, well, does fluorine or iodine win out? And it turned out chlorine wins out because it's like the give or take is working out best for the second row. The only way you maybe can reason this out is that chlorine maybe doesn't grow as much in size, but increases in that effective charge. And so we have here that same issue of from top to bottom, an increase in effective charge is favorable for electron affinity, but the increase in size is unfavorable. And so it just turned out that the third row is best. But I don't think there's any reason to memorize that the third row is best, but just that there's a give and a take, and in this case, the third row wins out instead of the sort of fluorine row or the iodine row. And so, so the third row is particularly more negative than the others, but they're all relatively favorable. So not a huge trend, not much of a trend from top to bottom. If you want to reason anything out, it's just the counteropposing Z-effective size trend that doesn't win out on the top or bottom side, actually in the middle. Okay, so chlorine in the middle wins out the effective nuclear, or the electron affinity. Okay, so let's come back to some cation configurations and talk about a few of these things here. So electrons in the ground state of zinc atom experience the lowest, so electrons in which subshell of zinc experience the lowest effective charge? So let's think about zinc. So zinc is the argon configuration followed by a 4s2 3d10. If we were counting valence electrons, we'd probably say just 2 valence electrons. This is somewhat helpful to remember, because if you remember these are the only 2 valence electrons, you would probably think those should be the first 2 electrons lost to make a cation. So if you're on a test forgetting, does zinc 2 plus, is zinc 2 plus going to be a 3d10 or a 4s2 3d8? You can probably be like, well, if it was a 4s2 3d8, we should have said it had 12 valence electrons, but it only has 2. And so we only lose these 2 electrons here, so zinc 2 plus should be an argon 3d10. And a 3d10 should have 0 unpaired electrons. So the unpaired electron count, like how many unpaired electrons does zinc 2 plus cation have, just says, well, take your D subshell, 5 of them, and put your 10 electrons in. And so when we do that, we have 0 unpaired electrons for our zinc 2 plus cation. Now that second question, we'll come back to the first one in a second, but the second question is really just getting at, do we think it's that or do we think it's 4s2 3d8? And if we thought it was this, then we would have had 2 unpaired electrons and thought something different in our electron count. So it's not this, so it's this. And so we remove the electrons from the biggest orbital first. Now, one of the reasons you can imagine that you remove from the largest orbital first is by thinking of which of the subshells has and experiences the lowest effective nuclear charge. And so for zinc, it's element number 30. So we have a 30 plus. And so again, if you come back to 1s, 2s, 2p, 3s, 3p, set of orbitals, and then you have the 4s versus the 3d. So this being a 3d. So if you compare the 3d, it's closer to the nucleus. It has fewer electrons in its way. Like the 4s electrons has all those other electrons absorbing nuclear charge. The 3d doesn't. The 3d is experiencing a much greater effective charge. So the 3d electron experiences a higher effective charge, and that's another way you can think about those electrons being harder to remove. And so the electrons being closer to the nucleus makes them harder to remove. Now, it made them harder to put in. Like calcium didn't put the electrons in the D subshell because of electron repulsion. So once we get to the transition metal block, though, we can start packing electrons into the D subshell. Once they're in there, harder to remove. And so it's easier to remove the 4s, which experiences a lower Z effective compared to the 3D subshell. So the 4s subshell, more electrons in its path, more electrons absorbing nuclear charge, so it experiences lesser of that 30 plus charge. So probably closer, if you do the Z minus core electrons, it would be only a +2 charge, but you can see more core electrons in the way than the 3D subshell. And so the lower effective charge is going to be experienced by the 4s electrons. So we end up with that 3D10 configuration as a result. And it's important to recognize that this isn't like some anomaly for transition metals. It's just the rule for cations is you remove the electrons from highest n with the highest L. From that largest orbital, it's the orbital that's experiencing the lowest effective charge. Okay, so let's look at lead 2 plus, lead 4 plus, or things that get into then being in like the P block that also have other electrons in the way. So let's go back to lead 0. I think the easiest way to get a cation configuration is to make sure you know first the neutral atom of lead's configuration. So lead's big, so it's preceding xenon. So xenon, element number 54. So that's 54 of the electrons. And then we go into the 6s2. And then if we follow the 6s2, we got to get all the way through the F block. So we got to go all the way through the 4f14. Then we got to go all the way through the D block. We got to go all the way through the 5D block. And if you're forgetting, is it 4f14? Well, we're filling across the first F block. So the first time you can have an F is the L equals 3. So the first time you can have L3 is when n is equal to 4. We're also then filling across the third D block. And so the third D block, think of D being L2. So the first time we can have L2 is 3, the next time is 4, so this would have to be the 5D. So sometimes you might forget these numbers on how do you get 4F versus 5D. So it's just the first time we can have the F is 4, and the third time we can have the D is 5. And then we finally get back to our 6p2 for lead. And you're also looking at carbon being a 2p, silicon being a 3p, germanium 4p, tin 5p, lead 6p. So if you're getting confused on is it 6s2 5p? No, it's 6s2 and the same number 6p2. And so then if you're thinking lead 2 plus, it's really good if you have this picture for lead 0, because the question becomes, well, which of these subshells do you remove first? And so I hope we can see, like if we ask how many valence electrons does lead have? Just 4, right? So lead only has these 4 valence electrons. So if you know lead has 4 valence electrons, you only have 2 subshells you can even choose from to remove electrons from first. Like we're not going to remove core electrons, so we're not removing the 5d or the 4f. So of the 6s and the 6p, which subshell is bigger? 6p. And so it's the highest n with the highest L. So it's not the highest L. If we chose the highest L, it would be the 4f. So of the highest n orbitals, which are 6, which of those has the highest L? Of course, whenever we draw the orbitals, I always draw the 2s and the 2p being bigger too. So it helps if you just think of the orbital size, the p being bigger than s. So the p is bigger than s, but we're only comparing the s and p because these are the ones that share the n equals 6 and are the largest shell, the largest orbitals. So these have lower n values, so we're not considering the d or f. So like a 6d orbital will be bigger than a 6p orbital, but we don't have the 6d orbital used by lead. Okay, and so that means we're going to go to this configuration for lead 2 plus. So lead 2 plus will be 6s2, 4f14, 5d10. So having lost the 6p2. And lead 4 plus will lose the 6s2. So it'll be a xenon, 4f14, and then 5d10. So again, if you think lead 4 plus, there's really no choice. It's the other 2 valence electrons that are left over. And so if valence electrons didn't matter, we would have probably learned some other count for them. So the valence electrons are the outermost, the ones most important in bonding, the ones lost first to make cations. Now, lead, I don't think is ever going to lose 2 more electrons. I don't think there's lead 6 plus that ever commonly forms. Lead 4 plus is pretty rare too, but it does form in like batteries, and like your car battery has lead 4 plus cations in it. Let's start class with this question on size so we can get removed from electron talking about size. Look at one more size trend, a couple more slides from chapter 7, and then we'll be into chapter 8 on Wednesday. All right, guys, that's it for today. Thanks for coming, and I'll see you on Wednesday. Let me see if there's anything worth talking about before we leave today.